going to get started with chapter 20, and chapter 20 is about electrochemistry. Okay, and what electrochemistry is, well, what the name kind of says, it's the relationships between chemistry and electricity, but really it's what is generated. There's some chemical reactions that actually generate electricity, and what electricity is the flow of electrons. So what we're going to do is we're going to look at that, and we're going to look at for both spontaneous and non-spontaneous processes. And again, remember we checked that out last chapter. We looked at the enthalpy and the entropy, and we used them to calculate at certain temperatures to get the Gibbs free energy, which told us the potential energy of a reaction. In other words, how much can we get from it? And a lot of times we get our energy as either heat or electricity. And so this chapter, we're going to talk about the electricity part. Okay. So when we're looking at this, what we need to really look at is when elements change oxidation numbers. Okay. When they go from one number to another. All right. There's some things to remember. I'm going to have right after this, if I had you last semester, I had you get a chart of ions, and that's mostly what their charge is. Really what their oxidation number is, the combining capacity. How many electrons they have available to give, or how many electrons they need. Okay, and so I'll have that chart in this, after this lecture, you'll see it. And most of the time that is what their charge is. Remember, if they're an element, if it's just pure aluminum or hydrogen or nitrogen, whatever, their charge is 0. Okay? And again, their monatomic ion is their charge. So if it's calcium +2, their charge is +2, and so on like that. There's some that never change, like fluorine never changes. It's always -1. Okay? Some of the halogens, like chlorine, is mostly -1, but it can be other numbers as well. Okay? Oxygen is pretty much always -2. Unless it's a peroxide, like hydrogen peroxide is H2O2. Not that common, so you can kind of count on oxygen as being one of the numbers you look for. And again, why are we using these? Well, we're going to find ones we don't know by using the ones that we know. Excuse me. Hydrogen is +1 unless it's a hydride, and if it's a hydride, it's the second element. It would be like CaH2, that'd be calcium hydride, and in that case, hydrogen would be -1. But you can pretty much count on hydrogen being +1 unless it's listed second, okay? And then one thing you need to remember when you have a compound, the oxidation numbers have to equal the overall charge. If it's a compound, it's 0. If it's an ion, it's whatever the charge of the ion is. If it's like phosphate, which is PO4, we need to have a charge of -3, okay? So whenever you're looking at the oxidation numbers, you can take the ones you know to figure out the ones you don't know and make sure they equal 0. This is kind of the same premise of when you're writing the formulas for compounds. You always crisscross the charges. When you crisscross them, then they end up equaling 0. So that's important to remember. Okay, so if we're doing oxidation numbers, and again, we're looking at reactions that are going to produce electricity. They have to be what they call oxidation reduction, or redox reactions they call them. Okay, if they don't exchange oxidation numbers, if there's no change, then they're not going to generate electricity. Okay, so that's the kind of reactions we need. Okay, here's one where we have zinc, and zinc by itself is a solid. Because it's just an element, it's 0. It doesn't have a charge. Over here, when it combines with chlorine, now it's +2. So that would be a change in oxidation number, going from 0 to +2. Here we have hydrogen. It's combined with chlorine, so it's just +1. And then over here, you can't see it, and I'm sorry about that, but it's plus H2 over here, hydrogen gas. It's hydrogen by itself, so its oxidation is 0. So now it's going from +1 to 0. So we have two of them changing numbers. We have zinc and we have hydrogen. The chlorine stays the same on both sides. It's -1. So it's not involved in that part. Okay. So if the oxidation number increases for an element, the element is oxidized. So in other words, if it becomes more positive. Okay. So zinc goes from 0 to +2, it's oxidized. If the oxidation number decreases for an element, then the element is reduced. Hydrogen goes from +1 to 0. So it doesn't have to become negative, it just has to become less. A common one that I always use is oil rig. Oxidation is loss. Okay, if it loses electrons, it becomes more positive, it's oxidized. And reduction is gain. You gain electrons, so you become more negative or less positive, whichever you would. And oil rig, kind of works for our lovely state of North Dakota. Okay, So here's another one. A species is oxidized when it loses electrons. So again, here's zinc. It was at 0 and it went to +2. So it's oxidized. It became more positive. The hydrogen went from +1 to 0. Okay, so it became less positive, or it became more negative because it picked up electrons, whichever way you want to think of it. But again, it's reduced. So the one that becomes more positive is oxidized. The one that becomes more negative is reduced. Okay, and then you got to change the names. This is funny. Okay, so zinc is oxidized, so it's called the reducing agent. Hydrogen is reduced, so it's the oxidizing agent. You know, it's like, really? Okay, whatever. But so if you're talking about the agents, it's opposite. So if something is oxidized, it's a reducing agent. If something is reduced, it's the oxidizing agent. And one thing you'll see, if oxygen is involved, it's pretty much always reduced, so it becomes an oxidizing agent. So that becomes, you know, but a lot of people think, well, oxygen would be oxidized, and don't think of it that way. Okay, it's looking at the charges. If you do that, you'll get confused. Okay, so when you're doing that, when you're writing out oxidation reduction, you write them kind of separately as two separate equations, and you can use them to balance equations. I'm not going to have you guys do that because I'm going to show you the slide of all the things you have to do to balance a redox equation. I'm going to show it to you, and we'll leave it at that. Okay, oxidation reduction, though, what you do is you write them as two separate ones. Okay, in this case, zinc went from +2 to +4. Okay, so it was oxidized because it became more positive. And so then we added, you can see if it goes from +2 to +4, +2 electrons. It had to have lost 2 electrons to go from +2 to +4. Iron, +3, over here it's +2. Okay, so it became reduced because it's less positive. And again, in the equation you had the 2's there, so this over here was +6 and this over here was +4. So that's why you have the 2 electrons. It had to lose 2 electrons to go from, and again, I'm just multiplying 2, like +3. This is +6 over here, this is +4 over here. So I have to have my 2 electrons here, so they'll balance out. Okay, and again, here's a better one. Now, I'm going to show you this. Don't write it down. I just want to show you all the things you would have to do if you're going to balance an oxidation reaction, redox they call it, or reduction oxidation or whatever. But this is a short version of it. You won't have to do them, but I just want to show you how crazy it gets. Okay, so first you make the 2 half reactions, and that's where we're going to quit. We're going to do the oxidation and the reduction, and then we're done. But then you balance the other oxygen and hydrogen, and then you balance the oxygen and hydrogen using water or hydrogen ions. Then you add electrons to balance the charges. Then you multiply the common factors to make electrons and half reactions equal. Then you add the half reactions, and then you simplify using common factors or converting hydrogen to hydroxide. If it's base, if it's acidic, you have to do the hydrogen to hydroxide water up here. So again, it gets really crazy complicated, and you always have to double check. That's important. We're actually just going to do this first step. Okay, but I wanted to show you, you can do them, and if you take an upper level, if you take an electrochemistry class, you'll learn how to do all this. But this is just kind of an introductory class, so we're going to get started on them, but we won't do all this. Okay, just you can sleep better at night knowing that, guys. Okay, so here's a half reaction method. Okay, we have over here we have manganese, potassium, and then this is, well, they don't tell you what it's combined with, but the most common thing to have, MnO4, this is permanganate. It's usually potassium permanganate. Okay, so we have the reaction, and these, they crossed out the spectator ones, you know, like if this was K, MnO4, and maybe it was K over here, they just crossed those out. So we just got the spectator, or we got rid of the ones that aren't actually involved. And one of the other things you'd have involved is water, because these are dissolved in water. They're aqueous. You can see AQ. So anytime you have anything dissolved in water, you're going to have hydrogen. So that's probably what's in here. Hydrogen, yeah. Anyway, not to worry. We're just going to look at the ions that are involved, okay? So if we assign oxidation numbers, okay, Mn, not magnesium, manganese, sorry, goes from +7 to +2. So here it's +7, over here it's +2. Carbon goes from +3 over here to +4 over here. So +7 to +2, that's going to be reduced, right? Because it becomes less positive. And +3 to +4, this one's oxidized. Okay, now I'll show you it better. Okay, here's the reaction. Okay, how did I get that +7? Okay, MnO4 has a -1 charge. So altogether, I got to make sure these guys, whatever this is, this one has to be one less. Well, if you look at oxygen, I know oxygen's -2, and there's 4 of them. So that oxygen's got to be -8. And again, this has 1 negative charge. So if you take that into account, this is -7. So that's why the manganese has to be +7. So if you look at this, this is +7, this is -8. When you get those together, you get -1, and that gives me my charge of my ion. Okay, that's where I got the +7 from. Okay, so over here, it's +2. That I didn't even have to figure out, it just told me. So if I go from +7 to +2, in order to do that, I have to make sure that I get rid of, or whatever, 5 electrons to get here. Okay. Now, for the C2O4, it has a -2 charge. Okay. So again, I have to figure out the charge. I know oxygen is 2, and there's 4 of them, so that's -8. Okay, and then -8 minus 2 is -6. So this side, the negative side, I guess we'd call it, is -6. So this side has to be +6. So +6 divided by 2 is 3. That's where I got the charge of the carbon being +3. Okay, so again, I'm using oxygen. I have 4 oxygen, and I know oxygen's -2. So there's -8 for oxygen, and then this -2 is the overall charge, so I knock off 2. So this side is -6, this side has to be +6. So, and there's 2 carbons, so 6 divided by 2. So I know the charge of carbon is +3. Well, over here, carbon is in carbon dioxide. Oxygen, there's 2 of them, so that's -4. So the carbon has to be +4. There's no charge here, so this has to equal 0. So positives and negatives have to equal to each other. So that's where I went from +3 to +4, where I got that. And again, it's becoming more oxidized. It becomes more positive. Okay, where did I get the 2 electrons from? Well, I got 2 here. If you look, it's C2, right? So I got a 2 here. So altogether I have +6. Well, if this is +8, there must be 2 electrons there. Okay. Over here on this one, I know its charge is +7, and over here its charge is +2. Well, how did I get that way? Well, I had to. So the other way to think of it, I probably messed that up for you, sorry about it. But these guys, +7 minus 5 +2, okay? Or you can see the one that's reduced has electrons on the reactant side. The one that's oxidized has electrons on the product side. That's maybe better, okay? And again, there's 6. This is 8, so I have to reduce this by 2, get rid of these 2, and that's why this one becomes more positive. So when you're looking at these half equations, the side that's reduced is going to have electrons on the reactant side. The side that's oxidized is going to have electrons on the product side. Okay, and again, so these are our half equations. Oops, sorry. Okay, so again, it's going to be 2 carbon at its +3 goes to 2 carbon at its +4. So it becomes more positive. I know it's oxidized. And again, electrons on the oxidized side. On this one, we have +7 goes to +2. It becomes less positive. Okay, it doesn't have to be negative, but it becomes less positive. So in our 5 electrons, so that's reduced. And again, if it's oxidized, you have the electrons on the product side. If it's reduced, you have electrons on the reactant side. And like I said, I always remember oil rig. Oxidized is loss of electrons. It's more positive. Reduction is gained. It gains electrons. It becomes more negative. Okay. And we're just about out of time, so we'll quit right there.